Welcome to the lecture series by the National Program on Technology Enhanced Learning. This is the lecture series in chemistry. Today it is the fourth lecture. We are going to discuss the molecular vibrations, but more importantly the underlying quantum mechanical model, namely the harmonic oscillator model. The last three lectures we have been going through a sequence of how to solve the Schrodinger equation rather with simple models like the particle in a one-dimensional box and the particle in a two-dimensional box. Today the model will be slightly more complicated, but I am not going to give you the details of the mathematics. I am going to give you only the results, and we try and understand the results as quickly as possible. We will try to assimilate the results rather than worry about the details of the mathematics. As I told you earlier, the importance of this approach or the reason for this approach is that we want to get to the chemistry part as quickly as possible. That is to deal with the atoms and molecules, with the atomic orbitals, and to understand the quantum mechanics behind that we must solve at least a few simple models. And today it will be another model, the model of simple harmonic oscillator, which is a very well known solved problem in mechanics, in classical mechanics. Many of you might have to recall the classical solutions or the methods. We will go along the way, and let me relate what that model has to do with molecular vibrations as we are interested in chemistry. Okay. So the lecture today is on harmonic oscillator and molecular vibration. How we relate these two things is the subject of today's talk. Okay. Let's recall the Schrodinger equation. You have solved the two simple equations, minus h bar squared by 2m d square psi by dx square plus v of x of psi of x is equal to E times psi of x. For a particle in one dimension, we assumed that this potential to be 0 in a certain region and infinity everywhere, and we had simple solutions coming out of it. The idea of quantization also coming out, and the wave functions. The solution gave infinite number of solutions, which we marked as psi 1 of x, psi 2 of x, etc. Okay. When you solve the differential equations of this kind, the Schrodinger equation particularly, the mathematical terminology associated with the Schrodinger equation is that it is an eigenvalue equation. Okay. The eigenvalue meaning there is a class of equations, differential equations in mathematics. Here the h is the Hamiltonian, and that's what makes it the Schrodinger equation, and the wave function psi as well as the energy E that we are looking for are called eigenfunctions. Psi is called the eigenfunction, and the constants that we obtain are called the eigenvalues. Okay. In this terminology, for the particle in a one-dimensional box, you might associate with them the psi n of x root 2 by L sine n pi x by L as the eigenfunctions, and the energy En, which you obtained as h square by 8 m L square n square, where the potential is 0 in the box of region of length L, this as the eigenvalues. Thus you can call the operator minus h bar square d square psi by dx square by 2m plus v of x, the operator as the Hamiltonian operator acting on a function giving you a constant times the function itself, and such solutions are called eigenvalue eigenfunctions solutions, and the equations are called eigenvalue equations. Also, one important point which I did not stress in the last lecture is that the solutions that we obtain for the H psi is equal to E psi, the solutions corresponding to different E values, for example here the solutions corresponding to n equal to 1 and n equal to say 5 or n equal to 2 and n equal to 10, for example, these solutions are called, they are orthogonal. Orthogonal in that the definition in this case of the orthogonality is that the integral of a wave function psi n of x, which is an eigenfunction of the Hamiltonian, for a particle in a box, the limits you might recall that we put x is equal to 0 to x is equal to L, and psi m of x dx. This integral is 0 if n is not equal to m. You might also recall that when an n and m are the same, of course this gives you 1. That's how we got this factor root 2 by L sin n pi x. That's what was called the normalization. Okay? But the functions belonging to different eigenvalues of the Hamiltonian operator are orthogonal, and that is something you have to remember. So we will introduce today's lecture the ideas as follows: the orthogonality of wave functions, the molecular vibrations, classical model for the harmonic oscillator, quantum model for the harmonic oscillator, and some general characteristics of the solution. Okay. I have just described this. You have seen that on the board. The orthogonality of wave functions for a particle in the box, as you see here, is that the integral of the two wave functions sin n pi x by L and sin m pi x by L dx integrated between the limits of the particle in the box, that is integrated over all the space available to the system, that integral is 0 for solutions which do not have the same eigenvalue. You can also prove this in general for degenerate systems, that is two solutions corresponding to two eigenvalues, both of which are the same, can also be orthogonal, but let us not worry about it now. I wanted you to basically appreciate the idea of what is called orthogonality with one example. We will see this often. Okay. So the summary is that the wave functions corresponding to two different energy solutions of the Hamiltonian are orthogonal to each other. This point must be remembered. Now we will go to the solutions of the harmonic oscillator and molecular vibrations. That idea was something that I did not stress in the last two lectures. So with that, we sort of come to one model problem, reasonably completely solved. Now we will look at the model problem of the harmonic oscillator and molecular vibrations. The reason why vibrations are important, of course, is that vibrations play a fundamental role in the chemist's understanding of how molecules dissociate, how molecules form. The dissociation energy of the molecule is associated with what is called the bond energy, and the bond energy is a concept that comes out naturally when you assume molecules to vibrate about an equilibrium as a spring, as a harmonic spring, or as an anharmonic spring. So the vibrational motion is fundamentally important in chemistry and is of course used in many instances, particularly in the field of spectroscopy, molecular vibrational spectroscopy. And those of you who have studied organic chemistry have seen infrared spectra of many molecules. The basis for that is molecular vibrations. In order to understand molecular vibrations, of course, one has to understand the model, or one has to predict a model underneath such molecular vibrational concepts. The other thing is vibrations are extremely important in one's analysis of molecules, detection of intermediates in chemical reactions in the form of spectroscopy, and also vibrations play a basic role in one's understanding of the details of molecular reaction dynamics at the most elementary or at the most fundamental level, that is at the level of Schrodinger equation, applying Schrodinger equations to molecules. So it is not necessary for me to stress this beyond this basic level introduction that vibrations are fundamental to chemistry. Okay. You can perhaps recall simple models of vibrations of simple molecules like water molecule or carbon dioxide. Let me just play one movie here. What are called normal vibrations of a bent triatomic molecule, water molecule. Later on, when we study spectroscopy, we will see that such molecules have 3 modes of vibration and so on. A simple illustration of what is meant by displacement of the atoms about their equilibrium positions is given in this movie. And what you see here is that the molecule vibrates about an equilibrium position and the center of mass here. And such modes are going to be studied using quantum mechanics. Okay. Another example of vibrations of a molecule is the carbon dioxide, a linear molecule. And you can recall that the stretching, the symmetric stretching of carbon dioxide about its equilibrium point, about its equilibrium position, is another example of how we visualize molecular motions. Okay. Vibrations at the level of what are called the normal modes in molecules are analyzed or studied using the simple harmonic oscillator model. And the rest of the talk, part of the rest of this lecture would concentrate on what is the classical model, and then how do we quantize and how do we get the solutions and so on. Simple harmonic motion is something again that you are familiar, a pendulum, a clock, the quartz clock that you have, the watches. I mean, there are many examples of what are called the simple harmonic oscillators. This is basically an oscillation about an equilibrium position such that the force that is responsible is proportional to the displacement from the equilibrium, and the force and the displacement are in opposite direction to keep the motion continue. A picture of a simple harmonic oscillator, you recall a pendulum. It keeps on moving back and forth, and obviously the back and forth motion in the absence of any other frictional energy loss is you can express that by a simple equation, namely the force that is responsible for when you displace the atom from its equilibrium position or you displace the clock from its equilibrium position. You have given it a certain force, and when you release it, the force that is responsible makes the pendulum go back to its equilibrium position, but by then it has picked up some kinetic energy and this kinetic energy keeps the pendulum oscillating back and forth. The relation is that the force and the displacements are vectors and are in opposite directions, and the force is equal to the vector with the force constant k, which expresses the strength of the oscillation or the frequency of the oscillation. Okay. The model for simple harmonic oscillator is that with this one can write the total energy of the oscillator. When we write the force is proportional, or when the force is equal to minus k times the displacement, and the force itself is the derivative, the negative derivative of a potential field associated with the harmonic oscillator motion, and that when it is written as k times the x, the integration of this gives rise, the integration leads to v of x is equal to kx square, the minus sign cancels off, by 2 plus a constant when you integrate on the side. Okay. The constant refers to the value of the potential when the displacement is 0. If the displacement is 0, let us assume that the species is in equilibrium and has the minimum potential energy, and that minimum potential energy, being a constant, is usually set to 0 as a scale. That is the scale with respect to which the potential energy is referred for displacements not equal to 0. So when you do this, the potential energy has a simple expression Bx is equal to half kx square. And if the oscillator is displaced by x and has been associated with motion, then its kinetic energy is obviously the mass of the oscillator and the derivative of the displacement square, that is the velocity, mu v square 1 by 2 as its kinetic energy, or in terms of momentum, the kinetic energy, which I can write as Ke as p square by 2 mu, where mu is the mass of the harmonic oscillator associated with the motion. This plus the potential energy of the harmonic oscillator represents the total energy of the harmonic oscillator, and one can write the total energy or the Hamiltonian in classical mechanics for the harmonic oscillator as p squared by 2 mu plus half kx square. As has been done earlier, now you go to the process of quantizing and start solving this as a quantum mechanical problem. Then the prescription that was given to you in the first or second lecture was that the operator, the p, the momentum has to be associated now with the operator called minus I h bar d by dx, and then you convert this into a quantum mechanical Hamiltonian. Then solve the Schrodinger equation that h psi is equal to E psi. That is the quantum problem associated with the classical harmonic oscillator. So what you see here is essentially the summary of that, namely the potential energy is a function of the square of the displacement, and for the constant set to 0 for the lowest value of the potential, this is parabolic. If you plot the potential energy as a function of x, what you have is a parabola. If you plot the potential energy as a function of, say, x is equal to 0, x can be both negative and positive, because if you choose one direction as the positive direction, the other side, the opposite direction, is obviously the negative direction. The positive or the negative value, you see the potential energy V is equal to half kx square is a parabola, if this is the 0 value. Okay. Depending on the value of the k, the parabola can be this way, or the parabola can be even this way, or the parabola is that, depending on various values of k. And I will leave it to you to decide whether k here, k1, k2, k3 each represent one of these graphs, for you to decide whether k3 is greater than k2 or greater than k1, or whether k1 is greater than k2, greater than k3. It is for you as an exercise. Okay. The potential energy is given by a bounded curve, and if this is the maximum displacement for any value of k, for example, let us take k3 as the harmonic oscillator potential energy. What does this maximum displacement mean? The maximum displacement means that the potential energy is maximum at that point, that is the turning point of the oscillator, and then the oscillator comes back again to go to the other side of the x. At the turning point it has no kinetic energy. Therefore what it means is that the Hamiltonian, when you write h is equal to p square by 2 mu plus half kx square, the kinetic energy is 0, therefore the energy, the potential energy, represents the total energy at this point or at this point. What about the value at this point? At this point the potential energy is 0 because there is no displacement. The oscillator has come back to its exact equilibrium position, and therefore what you have is there is no potential energy associated with. What you have is all the energy H is p square by 2 mu. There is no potential energy involved. So what you see as a harmonic oscillator with a constant energy is that it is oscillating in such a way that the energy is transferred between a kinetic energy and a potential energy such that the total remains a constant, but at the extremes the potential energy is maximum, right at the middle the kinetic energy is maximum, and everywhere in between it is possible for the oscillator to have a combination of energies such that the total is a constant value. Okay. Now that is one important point. The second important point is that the oscillator can have an energy, a constant energy like this, or the oscillator can have a constant energy like this. Classically any energy is possible depending on how much of it the displacement, maximum displacement is, assuming that things are harmonic. When the potential energy is when the displacement is very large, you don't expect the motion to be harmonic. This graph may not be satisfied. This may not be the right expression for the potential energy. But assuming things are harmonic, any possible displacement is any value for the displacement is possible, and any value for the energy is possible. We will see such things don't happen when we go to quantum mechanics. Okay. So the quantum Hamiltonian now, when we quantize the classical Hamiltonian for the harmonic oscillator, p squared by 2m plus half kx square, when p is replaced by minus I h bar d by dx, the Hamiltonian is minus h bar square by 2m. This is, I've been using the symbol mu. M is the mass of the oscillator, so the symbol m and mu are often used interchangeably, and just in the next few slides I will show you what mu represents. It's minus h bar squared by 2m or 2 mu d squared by dx square plus half kx square. Okay. What is the relation now between this and the molecule's vibration that I've been talking about? Now if you think about a diatomic molecule as two atoms with mass m1 and m2 connected to each other by a bond which you can imagine to be a spring, and if the molecule doesn't vibrate, it has no vibrational energy, you call this as the equilibrium, the position of the molecule, then the bond distance, the bond length between the centers of masses of the two atoms m1 and m2 is d. During vibration the spring is extended or compressed as the molecules undergo vibration. The length d changes by x, positive or negative, and the spring motion for small values of x relative to the value of d is modeled as a harmonic oscillator. The kinetic energy of the diatomic molecule as the two atoms vibrate about their equilibrium positions, okay, as the two atoms are going away from their equilibrium positions, each displacement of the atoms x1 and 2, namely x1 and x2, lead to the individual kinetic energies half m1 dx1 by dt whole square. This is the velocity of the atom 1, and this is the velocity of the atom 2 with the masses m1 and m2, and the potential energy of a vibrating diatomic molecule is essentially the potential energy due to the separation between the two atoms in the molecule. If they are farther apart, the interaction between the two is less. If they are closer, the interaction between the two is more, and so on. Therefore it is a separation between these two, and that is essentially the difference between the two displacements. So the potential energy depends on what is called the relative displacement x for the diatomic molecule, and it is exactly in the same form as that of the harmonic oscillator, with of course a different constant k prime characteristic of that molecule. The potential energy is only a function of the relative displacement of the two atoms. If we neglect the molecule as a whole, when it is vibrating as a whole, if the molecule is translating, if we neglect that motion, if we neglect the motion of the molecule as it vibrates its translation, then it is possible for you to rewrite the kinetic energy of the molecule in the form of a reduced mass times a velocity associated with the relative displacement. Okay. This is elementary classical mechanics. I will not derive it. I will give you the answer. The answer is that when you neglect the overall translational motion or the motion due to what is called the center of mass, the kinetic energy is no longer a sum of two terms, but it is given by a reduced mass mu and the velocity dx. Let us write that down. V of x for a molecule is that it is half k prime x square, where x is x1 minus x2 whole square, and p square by 2 mu is the kinetic energy of the diatomic molecular vibration, where p is m into x1 minus x2 dot velocities. It is a relative displacement, relative velocity. So what you have is, in the diatomic molecular Hamiltonian, you have only one coordinate, namely the displacement from equilibrium, the overall displacement from equilibrium, determining the Hamiltonian as p square by 2 mu plus half k prime x square, where mu is now the reduced mass. It is not the mass of the harmonic oscillator like you had earlier. It is a reduced mass given by the expression m1 m2 by m1 plus m2. Okay. So the analogy to harmonic oscillator, with this Hamiltonian being the molecular Hamiltonian and this being the Hamiltonian of a simple harmonic oscillator, the analogy is very clear, that whatever was the mass of the harmonic oscillator is now replaced in the case of a diatomic molecule by a reduced mass. This mu is called reduced mass. Okay. And the k prime is a force constant that is associated with the bond strength between the two atoms in the molecule, how quickly they vibrate or how slowly they vibrate, what is the relative strength between the two atoms, and so on. So there is information now, when you solve this problem, there is information that you will obtain about the strength of the bond or the strength of the harmonic force constant of the oscillator. Okay. Thus, if you compare the two problems, the harmonic oscillator problem with the kinetic energy p square by 2m plus half k x squared, and that of the diatomic molecule with no translational energy in place, we neglect that, and also no rotational energy. We do not consider the molecule to be rotating. Let us assume that the molecule only undergoes vibrational motion. You see that there is already a relation between the two. The Hamiltonians look exactly the same, and therefore the solution of the harmonic oscillator problem throws light on the vibrational motion of the molecule, and that's the reason why we are interested in it as a physics problem. No, quantum mechanics as a physics subject is not of interest to us. Here we are looking at how to apply this to chemical systems, and therefore our solutions will be directly involved, or will be only those which are of interest to extensions to molecules. Okay. The Schrodinger equation now is, having written the Hamiltonian, the Schrodinger equation H psi is equal to E psi can be written rather immediately with minus h bar square by, let's use 2m for the mass of the oscillator, and we know that we have to replace m by mu in the case of a diatomic molecule. D square by dx square plus half kx square times, or acting on psi of x, is equal to E psi of x. Since we have not imposed any boundary on what energy or what the x value of the oscillator is, that is how far away it is from equilibrium, the theoretical limit, it doesn't make any sense, but we will still write it. The theoretical limit for the x is from minus infinity to plus infinity. We know very well that that's not going to be harmonic. When x is very, very large away from the equilibrium, you try to swing a pendulum far away from it, I don't think it ever comes back to its equilibrium position. It loses it. Maybe it will even break, okay, if the energy associated with the pendulum is very large. But for a model, let's assume that the x values are either extremes of the x values, and when that is not true, we will say the harmonic oscillator is not a harmonic oscillator, the oscillator is an anharmonic oscillator, and so on. For a theoretical model, let us just fix the value of x. This is the boundary. X is, well, all the way from the negative infinity to positive infinity, and with this boundary we want to solve this equation. I cannot give you the method of solution of this equation in half an hour. It's not possible, and the method is also complex if you haven't understood or studied the method of solving such differential equations using what are called infinite series method or power series method. Such methods are usually taught at the second or third level of mathematics courses, and we are not going to worry about how to solve this equation, but rather concentrate on what are the solutions and how do we understand the solutions. As I told you earlier in the first lecture or the second lecture, if you do not know how to solve a differential equation and are given a solution for the differential equation, what will you do? Substitute that solution in the differential equation and see that it satisfies, and try and at least convince yourself that the solution makes sense, even though we may not be able to write it down immediately. The solution is rather complex, so let me write down parts of it one by one. Like the particle in a box, this equation also gives many, many solutions. That is, many psi's and many e's. How many? In principle, infinity. What is also interesting is that E does not turn out to be any possible value, but E is given by a certain number called the quantum number, just like the particle in a box, where the n turned out to be a quantum number because we imposed the boundary conditions on the particle in the box. E is infinite number, but not any possible value of E. The value of E turns out to be n h nu n plus a half. H is already here in the differential equation, minus h bar square, h by 2 pi is there. So when you solve, the h comes out. What is nu? Nu is 1 by 2 pi square root of k by m. Okay. K is the force constant associated with the potential, and m is the mass of the particle of the oscillator associated with its kinetic energy term. What are the values of n? Here, to our surprise, n equal to 0, n equal to 1, n equal to 2, 3, only integral values, but including 0. In the particle in a box, n equal to 0 was not an acceptable solution because that left to a wave function which is 0 everywhere. And all these solutions have a solution psi equal to 0 as a trivial solution. Okay. But in the case of harmonic oscillator, n equal to 0 does not give you a trivial solution, it still gives you a finite solution. Okay. We will see that. Okay. So the energy En turns out to be h nu into n plus a half, where n is a quantum number. So if you write the harmonic oscillator energies in quantum mechanics, you have E0, which is half h nu, E1, which is 1 plus a half, so 3 halves h nu, E2, which is 2 plus a half, so it is a 5 halves h nu and so on. So it is always the half integral number of the corresponding n value. E2 is n is 2, so 2 plus a half. Likewise any number, but there is nothing in between E0 and E1, so there is quantization. It also means another thing. If you recall, the particle in the box E2 minus E1 was n square, h square by 8 ml square, n corresponding to 2 is 4 and n corresponding to 1 is 1, so it is 3 h square by 8 ml square. And E3 minus E2, that is the difference between successive energy levels. If you look at this, was h square by 8 ml square, 3 is 9, n square is 9 and 2 is 4, 9 minus 4 into 5. You see that these are not the same. And likewise when you go on calculating the difference between successive energy levels in the particle in the box, you will see that this energy gap keeps on changing. In the case of harmonic oscillator, the successive energy levels differ by the same amount. E1 minus E0 is h nu, E2 minus E1 is again h nu, E3 minus E2 is again h nu, that is harmonic oscillator energies are equidistant. Harmonic oscillator energies are equidistant. The particle in the box energies are not equidistant. Okay? This is as far as the energy is concerned. What about the wave functions? Let's keep the solution h psi is equal to E psi at the top, and what I just now said means that h psi n is equal to E n psi n. Corresponding to various values of E, there are different values of eigenfunctions. What is psi naught of 0? The solution for psi naught of 0 turns out to be, but for a constant, this is a proportionality, turns out to be e to the minus alpha x square by 2. Okay. What is the value of alpha? Alpha is given in terms of the constants we already know, namely k m by h bar square. Okay. Just let us do a simple analysis. Okay. Exponential of minus alpha x square by 2. What should be the dimension of the whole thing? Exponential should not have any quantity which has dimensions overall. If x has the dimension of the length, x square has the dimension of length square, alpha must have the dimension of 1 by length square, so that this whole quantity does not have any dimension. Let us see whether dimensionally that is what you get. What is the dimension of k, being a force constant? Okay. K, recall that kx square represents energy, and energy is ml square t to the minus 2. The force constant has the dimension m t to the minus 2. Okay. And the mass here, let us do the dimensional analysis. The mass here km by h bar square, so if you do that, m t to the minus 2 and m for the mass, and the h bar is m l square t to the minus 2 whole square, and then you have the square root of this. Okay. So what do we get? M square goes away. Okay. Sorry, h bar is t to the minus 1. Okay. ml square t to the minus 1. So t to the minus 1 whole square goes away, and therefore what you have is square root of 1 by L to the 4, or you get 1 by L square. Okay. So dimensionally, alpha e to the minus alpha x square by 2, this particular quantity is dimensionless because x square is L square, alpha is 1 by L square. So solution makes sense dimensionally as of now. we do not know how to do this. At least I am not going to tell you how to get this solution. So the only thing that you can do immediately is to see whether this solution, when you substitute in the differential equation minus h bar square by 2m d square by dx square plus half kx square times psi of x is equal to E psi of x, gives you, when you substitute this is the psi naught, therefore if this is the solution, if this is the solution you want to substitute in this equation, you must get the value E naught psi naught of x, where what is E naught? E naught, we just wrote the expression n plus a half h nu with n equal to 0, so E naught is half h nu. I will leave that as an exercise for you to verify that this equation, differential equation, with the solution psi naught being e to the minus alpha x square, with alpha being defined as square root of km by h bar square, when you substitute that you get everything right. With nu also given as 1 by 2 pi, you remember nu was given as 1 by 2 pi square root of k by m. Okay. So this is for you to verify. This is only one solution. What are the other series of solutions for the harmonic oscillator? The next one is psi 1 of x. Let me do 1 and 2 solutions and then we can generalize it to what the solution should be. Psi 1 turns out to be proportional to 2x e to the minus alpha x square by 2. Psi naught earlier was, psi naught of x was proportional to e to the minus alpha x square by 2. In fact, the whole infinity of solutions psi n of x, all of them have some function of x, a polynomial of x to some order, multiplied by e to the minus alpha x square by 2. Okay. That turns out to be the harmonic oscillator solution. I am always writing a proportionality sign. I am not writing the exact form. There is a constant which you need to put in here. We will show that in a minute. Okay. All these solutions have this exponential of minus alpha x square by 2. Now, what is the value of this as x goes to very, very large values? The exponential alpha x square minus alpha x square goes to 0 very quickly as x increases, either as a positive x or as a negative x, because it is x square by 2. Therefore, this function goes to 0 very quickly for large values of x. No matter what the value of this function is, this always goes to 0. And exponential, this exponential goes to 0 much more quickly than any function for sufficiently large values of x. Therefore, this function actually dies down extremely quickly for large values of x. So the solution makes sense that the likelihood of finding the particle at very large values of x is actually very, very small, because when you take the square of this function in a small region, that is what is called the probability of finding the oscillator in that region. And if this function is small, the square of this function is small, therefore this function goes to 0 very quickly. The probability of finding the oscillator at very large values of x away from its equilibrium, that possibility or that probability goes to 0 very quickly. It's not 0, but it's very, very small. Okay. So the solution makes sense in terms of a boundary condition. The second part is that what is this polynomial? How does it change for different values of n? Let me now write down the general solution as you have here. The value for any n, we talked about n equal to 0, n equal to 1. The value for any n, the function has this particular form, namely a constant, a capital N, but that constant depends on the quantum number that we choose, multiplied by a polynomial function h n with the functional argument being root alpha x and the exponential minus alpha x squared by 2. Alpha I have already written down as square root of km by h bar square, and nu I've already given as 1 by 2 pi square root of k by m. Okay. What are these polynomials? Okay. You see that for n equal to 0, the polynomial is h naught square root of alpha x, okay, which, as I have in the slide here, h naught of x is a constant 1. Okay. It doesn't depend on root alpha or x, simple 1. What you have in that slide is h1 of x as 2x. Therefore, the harmonic oscillator solution h1 of root alpha x is 2 root alpha x. Okay. What you have here are hn of x, and these are called Hermite polynomials. The Hermite polynomials turn out to be part of the solutions of the harmonic oscillator. It can be shown, I mean, I don't want to do it here. It will take about 2 hours to do that mathematics, and it's also not interesting, not important for us, because we want to see how to use the solutions in chemistry. The solutions, Hermite polynomials, are obtained by solving what is called the Hermite's differential equation, which is what the harmonic oscillator Schrodinger equation will be reduced to when you do the mathematics right. We are giving the final solutions. The Hermite polynomials are, in principle, it's an infinite number of polynomials, and they are increasing powers of x as you have them here. For example, Hermite polynomial of order 0 is a polynomial of degree 0. Hermite polynomial of order 1 is a polynomial in x of degree 1. It's just a function of, it's simply x. Order 2 is a quadratic function. Order 3 is a cubic polynomial, and so on. So there is a direct relation, whatever is the order, that is the highest power of this polynomial, and there is a way of generating this polynomial through what is called recurrence relations between these polynomials. Between Hermite polynomials hn, hn minus 1, hn plus 1. Therefore, one can generate this table for n equal to 20 in no time. Okay. Again, that is not of interest. What is of interest is the nature of this polynomial. Okay. You see, the first polynomial h1 of x is 2x, which is a function of x, but when x becomes minus of x, the function becomes minus. The next one, h2 of x, is 4x squared minus 2, which for both positive and negative values of x has the same value, 4x squared minus 2. So whether x is plus x or whether x is minus x, the function is the same. You go to h3, it is a cubic 8x cubed minus 12x. Again, this function becomes the negative of the function for negative values of x. So you see that this series alternates between functions which do not change sign and functions which change sign as you change x from minus to plus x. Such alternating sets are called odd and even sets. The function h naught is known as an even function of x, the function h2 is known as an even function of x, h4 is known as an even function of x, whereas all the odd functions h1, h3, h5, etc., they are all called odd functions. Okay. So the relation here is, if this hn of x is minus 1 to the power n of hn of minus x, okay, meaning that when n is odd, the function becomes the negative when x becomes minus negative, the minus of the x value. So this is something that will again be important when we go further. So all these numbers are, they can be easily generated. I don't think you need to remember any of these, but the point is you must remember that the power, the highest power of the polynomial is given by the order, as well as the fact that the order is odd or even depending on whether the quantum number is odd or even. Okay. The constants n which were associated with the wave functions are called the normalization constants, and they are obtained in the same way that we did the normalization constants for the particle in the box. What we did was psi n of x, psi n of x dx. For the particle in the box, the system's space was 0 to L. For the harmonic oscillator, the system space is x is equal to minus infinity to plus infinity, and this is, you set it equal to 1. And when you obtain this condition, that the probability of finding the harmonic oscillator anywhere along the regions that it can access, if you add all those probabilities, that it should be 1 is what is expressed by the normalization condition. Okay. And it's, as an exercise, you can obtain n. Let's do, when you write n as the expression 1 by 2 raised to n factorial alpha by pi to the power 1 by 4, we can do this for n equal to 0 and 1 as a simple example. When n0 for the wave function psi of 0 is of course raised to 0, 0 factorial, these are all 1. So what you have is alpha by pi to the power 1 by 4. n1 is again can be written easily. When n is 1, it is 1 by root 2, 1 factorial is 1. So what you have is n1 is 1 by root 2 alpha by pi to the 1/4, and so on. There are, by substituting the corresponding values of n, you can generalize you can generate all the normalization constants, and therefore the solution psi n, let's summarize. The solution for the equation h psi n is equal to En psi n of x for the harmonic oscillator, as the wave function psi n being the normalization constants n and the Hermite polynomial root alpha x e to the minus alpha x square by 2 as the eigenfunctions and the eigenvalues En as h nu times n plus a half. These are the eigenvalues. N is 0, 1, 2, 3, etc. Therefore, the energies are quantized. Energies are quantized, and energies are equidistant and are equidistant. So let's summarize this now. We will look at the remaining parts of the harmonic oscillator, the graphical representation of these wave functions, and the graphical representations for the probabilities, etc. in the next lecture. The most important point is that the solutions that we have obtained for the energies and the wave functions, the solutions exist even when the quantum number is 0, that is, even when we associate with the harmonic oscillator no motion, of no energy due to motion. Okay. There is an energy which is not 0 even when the quantum number is 0. That means the oscillator is never at rest, it keeps oscillating. The position and momentum of the oscillator, no matter what its energy is, cannot be simultaneously determined, cannot be determined simultaneously. If the oscillator is at rest, we know its exact position, and we know that the momentum p associated with the oscillator is also 0. Therefore, we seem to have knowledge which is forbidden in quantum mechanics according to Heisenberg's uncertainty principle. So the fact that the harmonic oscillator energies are non-zero even when the oscillator has a quantum number equal to 0 means that the oscillator is never at rest, and we are quite happy now that it is consistent with the Heisenberg's uncertainty principle. The second important thing, you recall that the potential energy was a parabolic function, limiting what is called the maximum possible value of energy for any particular motion. The wave function, on the other hand, for the harmonic oscillator does not vanish anywhere in between except at finite points. The boundary for the oscillator is essentially infinity, because exponential of minus alpha x square is never 0 except when x is plus infinity or minus infinity. So this function may have some roots, but the product apart from those roots, the product or the wave function is never 0 throughout the boundary, that is even outside the potential boundary. It appears that the wave function can be, the particle can be obtained, the position can be located even outside the region of what is called the classical potential boundary. And that means the squares of the wave functions are non-negligible in regions outside the potential boundaries. It leads to an interesting phenomenon called tunneling. Again, we will not do tunneling here. Tunneling itself is a phenomenon that one has to study carefully. The chemistry that we study does not require an understanding of tunneling right now, so let me just mention that and leave it. And obviously when you associate this with molecular vibrations, the vibrational energies of the molecules are quantized in the harmonic limit. Let me stop here and we will continue with the harmonic oscillator motion and representation of the wave functions and the squares in the next lecture.